In this video, we're going to describe and analyze a basic low-pass filter. Now, low-pass filters are found in many electronic applications. You might use them, for example, for noise filtering or switch debouncing or many other reasons to use them. And there are many types of low-pass filters of varying complexity. You can use active circuits and integrated circuits to make a low-pass filter, or you can make one using simple passive components. In this video, we're going to discuss the most basic of low-pass filters, which is a simple resistor-capacitor circuit. So imagine that we have a circuit, and we have a voltage in to our circuit, and we construct a resistor and a capacitor like this, such that we then have a voltage out over here with a resistor of resistance R and a capacitor of capacitance C. So what we want to know is, given a particular voltage in, which may be a step function, or it may be a sinusoidal function, or it may be some complex combination of these, what do we get for V out? Now, there are easier ways to analyze this perhaps, but we're going to go back to kind of the basic mathematical definition of capacitors and resistors. You know, for example, that for a resistor, a purely resistive load, V equals IR. And in our case, we're going to define the voltage across the resistor as VR, so V sub R. So we'll say that V sub R equals I sub R, the current going through the resistor, times the resistance. For a capacitor, if you remember, the charge on the capacitor, the voltage on the capacitor, the change in that voltage is related to the amount of current flowing through the capacitor. In particular, we know that for a capacitor, I, the current, is equal to the capacitance times the rate of change of the voltage over time. And if we call the voltage across the capacitor V sub C, then we see that, let's see, I sub C, the current through the capacitor, is equal to the capacitance times dVc dt. Now, in our circuit, if we assume that there's no current actually flowing out through V out here, or through the leg that leads to V out here, then that means that the current flowing through the resistor is the same as the current flowing through the capacitor. And if we go around the loop and do our voltage laws, then we know that the voltage in has to be equal to the voltage drop across the resistor plus the voltage drop across the capacitor. So using all of these, we can come up with an equation that models our little RC circuit right here. So setting the two currents equal to each other, that means that VR over R, that's from this equation here, is going to be equal to C times dVc dt. That's just setting the two currents equal to one another. And then